give me a sign. Thank you all for being here tonight again, despite the great sunny weather outside. You made it. So I have the pleasure to introduce Daan Gerits, who is going to talk about structuring, modeling, and managing big data projects. And the previous speaker was an academic who also rolls up his sleeves, but this is the other way around. This is somebody really from the trenches who's been doing big data for a decade. Can we say
more
that?
or less,
Maybe
yeah.
even more or less a decade. He's also one of the organizers of bigdata.be. For those of you who really get interested afterwards, is a meetup event happening regularly. So you can ask Dan about that too.
Sure.
And he brought some geospatial toys with him that you will all have to work with later on, right?
Yes.
So without further ado, Dan, the floor is yours. Have
Okay.
a nice evening and enjoy the big data from the trenches and all the modeling. Go ahead, Dan.
Hi everyone. So first a warning, I'm a guy who will be hopping around a lot. So yeah, sorry for that. As Ton said, today we are going into like what big data structuring actually means. Like in previous talks, you have heard about big data or got an introduction to what big data was. Today we are going to look at what the techniques are, why or what makes big data different from a technical point of view. We're going to look at the anatomy of distributed systems, or distributed data systems especially, because when you deal with a lot of data, or when you have to work with data that's coming in fast or is very diverse, you need to have a system that can cope with that load, that can cope with those characteristics. The second thing that we're going to look into is data at scale. So what is so different in working with big data? Why is it so different? What makes it different than what we did in the past 10, 20 years? The third part is about data models. So we are going to have an overview on the different data models that currently exist, the most popular ones actually, and give some examples and some of the characteristics. So you know that if you need to do a project, that you can make an educated choice into which data model suits your use case the best. And last but not least, I always try to give some advice from things that I have learned during my time as an engineer, data architect. So it might be that this is too much for this session alone, because I heard there was going to be some pizza, which means that we are going to stop at a certain point. If there is more, I will be back on Thursday. Thursday is going to go about integration in your organization. But it might be that if we do not complete everything, that we just take a part over. Because in my opinion, this is the meaty part. This is the fun stuff. The integration, it's something that you have to do in organizations. Okay, so let's get started. Let me introduce myself for a second. I will go very, very quickly over this. So my name is Daan Gerits. I have been a big data engineer and a big data architect for the past 10 years almost. I had a few startups, but I'm truly passionate about engineering and especially about data engineering, and more recently about real-time data engineering. I'm also the co-founder of bigdata.be. So 7 years ago, a few of us came together and we just said, like, it would be cool to share war stories. So let's continue coming together and tell what we have been doing in real life. Those 7 back then grew out to 2,500 right now. So we still do meetups, so if you like to have more information, if you want to talk to like-minded people, please do come along and we'll have a fun time. The anatomy. So what makes, or what technologies or principles do we use when we are using big data? Right? And to do that, I have a little exercise for all of you. So I brought some Lego bricks, and the idea is that each and every one of you takes out a hand or more or whatever out of it. The Lego bricks are considered to be the pool of data that we have. You don't have to run away. This represents the pool of data that we have with all the different aspects of the data. So the variety in data you can actually see through the color, through the size of the Lego pieces. It's funny to see that everybody just grabs one hand. So by the end you are allowed to create your own sculptures with it. It's always fun. So when you look at these bricks, if I ask you what are the correct... Okay, I will give you the box. Do you want one? Okay, so now all of us are part of a distributed system because we have distributed all these blocks among all the participants of the system. When you look at these blocks, everybody doesn't necessarily have the same amount of blocks. Who of you has a block like this? Okay. If you need to do a count, if you need to analyze this block for some reason, now all of a sudden we have how many people that have the same block, the same kind of data, and can perform that analysis? This is something called replication of data. I've replicated the same block among different people, the same piece of data among different people, so they can have a look at the data and analyze what kind of block this actually is. This is called replication, replicating data. And most of the time we do it because if some of you that have this block stand up and leave, there will still be enough people around that can actually do the processing and that can do the analysis. So replication is used to improve reliability and fault tolerance. So I explained you copy data across multiple physical nodes. In this case, we are the physical nodes, so that's a bit easy. And the purpose of a distributed system is to create these replicas, but also to keep them in sync. If something changes to this block, right, then it needs to change on all different sides, because otherwise the characteristics of the block are not the same anymore. Now, what you can see is that not everyone has that block. Not everyone has the same data. Not everyone has the same group of blocks. I can see blocks like this, for example. There are probably not many people that have a block like this. That's a double one. So, certain data is available on certain nodes. Because if you would copy all the data to each node in the system, that would not work. Because then the most amount of data that I could actually store is the amount of data that one single node can store. And that's not, that's not a scalable system. That means that you're limited by the amount of, or the capabilities of one specific node. So instead we're going to split it out. Instead we're going to partition or shard our data. I'm going to give you slightly different data than I will give you, then I will give you, then I will give you. So why do we do that? We do that to scale data systems. to have the ability to have multiple nodes with diverse data on their system or on themselves, in order to do the processing on parts of the data and not all the data at once. This is called partitioning or sharding, but most of the time in distributed systems, partitioning is the name being used. What is important is that you will use a logical partitioning key. What does that mean? At some point, I need to know where I have put which records. Now, in this case, I just handed out and I allowed you to grab everything out of the box. But in reality, I'm probably going to say like, all this kind of blocks are going to you. And all this kind of blocks are going to you. Because then you can only take care of that specific problem space, of that specific domain space, which makes it easier and faster for you to work on that. Right? Because you do not have the variety that you would normally have. Now, why do we do these things? We do these things to build a distributed system, to make a scalable system. Now, there's one thing that is also interesting. Look around at the blocks that you have. Count how many you have. And you will see that there are some people that have 1, 2, 3, 4, 5. There's one guy with a box over there. If I would ask you to count how many blocks you have, how long would that take? Well, it will be seconds for you, but it will be hours for him over there. Well, maybe not hours, but enough time for you over there. So if we do a computation, if I say like, okay guys, now do the count and come back to me the moment that you have done your count, then all of you will have to wait until he is done. That's a problem in a distributed system. That means that there is something wrong with the partitioning, right? And that's one of the problems that you very, very commonly face when you're implementing data systems in larger organizations. The fact that you have skewed data, as it's called. So we can look at the load. Yeah?
Sorry, I have a question. So in some of the cases, there are people that have exactly the same
Yeah.
pieces of work. So basically, when you replicate data, there should be also a key that you don't replicate twice the same data to the same participant, or not exactly.
In this case, that could be the white blocks. That specific block can be, for example, a person or an entity type, as we say. It doesn't necessarily need to be like the exact same block, right? But it's true, you need to be aware that you do not make duplicates on the same node. But usually distributed systems know about that, and they have awareness. They not only have awareness on the nodes, they not only have awareness on where the data is stored on a specific node, they also know where that node is in the data center. And in some larger setups, they even know where the data is across data centers. And this is important. Usually you want to optimize, for example, where your data is stored in order to minimize the risk, or mitigate the risk in this case. Because if I put it on one node, so if you look at a data center, who of you has ever seen a data center from the inside? Yeah? So imagine like these closets sitting there with multiple machines in them, up to 42 or even more. Just nodes in there. If something goes wrong with that whole rack, and power distribution is being cut from it, or network connection is being cut from that rack, I immediately lose 42 nodes. So when I store data, sometimes some technologies allow for what is called rack awareness, or data awareness, or location awareness, where the algorithm that is going to do or split out the data across multiple nodes will take that into account and will make sure that there is one replica on another node and there is another replica on a node in a different rack. right? In order to make sure that your system does not go down. So all of these distributed systems are made with one thing in mind, and that's expect failure. Expect that something goes wrong. We are only human. We make mistakes. Humans make mistakes. But we need to recover from them. And it's very hard to recover 1 petabyte of data from tape or CDs or whatever. So looking at load, this is quite an important characteristic of your data system that you're designing. Because your load, your system, can either be optimized to be read a lot, it can be optimized to be written a lot, or it can be optimized to be balanced. The balanced one is the hard one. And this is all driven by use case. Sometimes business will come to you and say like, okay, we need a system where you want to track like millions of devices and you want to know where they are. That actually means that it is a write-heavy system. Because every time that device changes location, I need to register it in my data system. The amount of writes are a lot more than the amount of reads that I will do in a system like that. The other way around is true as well. There are systems where you have a lot of reads instead of a lot of writes. Look at a website, for example. The pages of a website, let's say that you could store them, or you store them in an image database. Reading the images is probably going to happen much, much more than writing the images. And you can optimize your system to do that really, really quick. Because you take the penalty when you're writing it, not when you're reading it. If you want to have a balanced system, that's a hard thing, because now you cannot take the penalty on either side. You have to take a bit of a penalty on both sides. And that makes it difficult to build a balanced data system. What is the most important part and what makes data or big data different from traditional approaches is that you really start with what you want to get from your system, not what you want to put in your system. That will become clear in the next chapter. So let's talk about data at scale. So a lot of times when I told people about big data, they asked like, okay, what is so different about big data? What makes data big data? Or when do we talk about big data? Is there someone who can give an idea on that? What is big data? Uh-huh.
Otherwise, it's just another list. I usually use this method to
Yeah.
understand if it's big or not.
There are other systems than Hadoop to work with big data. The biggest thing is that, who of you has heard about the 4, 5, I think up to 72 Vs? Yeah? So who agrees with this? Everyone? Everyone agrees with this? I don't. I don't agree with this. Do you know why? Because for me, big data is all about new ways of thinking about data. And those Vs, and I don't know how many Vs you can actually come up with. I think the record is indeed 72. There was a search engine before Google. Who remembers Alta Vista? Everybody used Alta Vista or Yahoo at that time. But Google found a way to do different things with their data. They figured out how they could make that data usable. And that's why they had those V's. That's why they had volume. That's why they had veracity or velocity or variety or whatever V. It's a consequence, the V's. It's not a real reason why we want to do big data. The moment that you start to ask different questions, the moment that you do not want to talk about segments anymore when you talk about your customers, the moment that you want to talk about the individual customer and what he needs and what he wants, at that point, you cannot talk about traditional systems anymore because they're not capable of doing that at that scale. At that time, you need to figure out different systems. You need to look at different systems that can actually cope with the volume of data, with the amount of transactions that go through. Don't worry, everybody says the 4 V's are big data. But keep this one in mind, because this is really like why you want to do big data. A lot of people look at big data and think about that it's about technology. It's not. Big data is not about technology. Big data is about coming up with new creative solutions to new or existing problems. So when I say think different, what does it actually mean? Well, on a business side, you're going to change the metrics you use to measure success. You're going to use reach, for example, to see how far you can outgo, how far you can go and touch people with your products or with your services. Operational-wise, you're going to automate processes. You're going to make it easier to handle data. You're going to make processes data-driven. You don't want to have a human anymore sitting there looking at a diagram, and if that arrow goes over there, then I have to press this button and the rest of the process starts. No, why would I do that? I just make a program that can analyze the data, and based on the data, it will trigger something. Making things data-driven, especially in enterprise environments, is challenging. Because most people have used data at rest. Most people know about data when it's just sitting on a hard drive. But there is a new kind of data, which is called real-time data, that makes it harder to think about. But it's so, so, so powerful. Because all of a sudden I can make decisions in milliseconds instead of having to wait for days in order to have some insights. The last one is that we can make things personal again. We can talk about the individual again. Because now we can give him or her the data that he needs, the insights that he needs to make a decision. And we can guide them. We can actually build services that they want. And this is not only customer-wise. This is also for the people that are in your organization. Controlling, right? A lot of people think about big data and saying like, okay, now I don't want anything. Know when I will be sick at home, and then they know this and then they know that. Okay. In all honesty, if you're working for a company and you're afraid of that, just leave. Because if you think that they're doing something like that, then it's not the right company, then they do not have the right mindset. You can do a lot of good with data. So when you look at how data or traditional approaches in data processing, then you had a supply of data. So data files sitting somewhere, a database, I don't know what. Or you could even have a process that generates data, an order process, for example. We would modify that data to fit in a data model, one generic data model for everything. The promise of a traditional transactional database. Create one model and store everything in that one model, because at query time, when you have a request, you just format, you explain your request to the system in a way that it understands. It will do the processing, it will look at the model and give you an answer. But everything starts with that one model. Well, it worked for a while, but the biggest problem right now is that a lot of these models have grown. They have a lot of legacy in them. Columns that are not being used, tables that are not being used. How are you going to store images in a transactional or in a relational database? Sorry. How are you going to store voice in a relational database or videos? So that becomes difficult. Even the kind of questions that we ask from a relational system or that we ask from a data system as a whole have changed. You don't want to look at queries and give me a list of everything this and that. We don't want to do that anymore. We want to do trend analysis. We want to see how data changed through time. We want to see how people are related, how products are related to people, and people are related to those products again. If you have to do that on a relational database, if you have to do that in the traditional way of working, it becomes really, really difficult because this model cannot cope with that. It's not meant for that. So when you look at the big data approach, it's perfectly fine to have multiple of these models. And as you can see, your request is not the place where all your computation is being done. All your computation is being done up front, and your data is modeled in such a way to answer the request in the best possible and the easiest way possible. If I have an API, it might very well be that I have a relational database sitting here that provides only that API. If I want to do network analysis, if I want to do social analysis, see how people are related, see how products are related to people and to other organizations, then I very much like to have a graph model in here, or graph database. Why? Because it's the fastest way possible to do that kind of analysis. When I want to have more documents and I want to do quick searches on those documents and similarity searches, everything that's not just like equal ones. Give me everyone where name is Daan, or give me everyone where name sounds like Daan. It's two totally different things. I just want to try one of them in a relational database. It's possible, but it will take you time and a lot of maintenance. So having the ability to take a supply of data, any supply of data, real-time, batch, doesn't really matter. Do the computations and come out with several models instead of one model. Because at that time, your querying will be fast. There's another consequence of this. When you look at traditional ways, when new data came into the system, we needed to figure out like what is the ideal way of storing this. And everything that we couldn't store, we would just throw away because it didn't fit in the schema. It didn't fit in the database. Right now, this is something different. In this model, you will store the data. You will store the raw data that you get, the raw events, the raw files that you have. You just store them as is. You're not going to try to do anything with them. You will just, the moment that you need it, you will know that you will have that data available. And that's the important part. For some reason I make a mistake further up, I can always go back to the raw data. Over here, if for some reason, let's imagine that marketing comes to me and says like, okay, right now I want to understand the impact of people wearing white socks on our sales figures. It's an imaginary case. but you have never tracked that information. Although it was given in the source, in your supply over here, you never took it into account in your model. So the best thing that you can do is say like, okay, we'll do that. You modify this process, and you modify your model, and you start gathering that metric. But that means that you can only have that metric from that moment in time when you made the decision to start gathering it. This is different over here. In this case, you have the raw data. So if someone says like, I want to know the impact of the White Sox on sales figures, you can actually say like, okay, no problem. Let's generate a model, a specific model, that takes that into account. Let's take the raw data that we already have and do our analysis on that and generate a model that can answer those questions. So where there was a lot of effort, I'm going back and forth on this slide because I like them. When there was a lot of effort over here to fit your data in a model, we're just saying, no, just dump it over there. Dump your data, and then we stop. We're not even going to look at it. Why? Because looking at it will just take time. And we don't know if you're going to need it. We're not going to model that into something because we have no idea that we will actually use that data. But the moment that a request comes in, we can say, hey, let's look at the data. And I have it available. That's the difference between the two different approaches, the more traditional approach and a big data approach. Anyone? So if you have questions, just raise your hand or start shouting. Start swearing. No? Okay. Let's dive into data models. Who of you has worked with big data before? I know already one person who knows, played with it. That's good. Anyone else who has played with big data? Or with any other technologies like Hadoop, Kafka, Spark, anything else? Nope? Okay, nice. Anyone worked with data systems before? Relational? Mostly? Also relational? Okay. So, me too, when I got from school, I also was schooled in relational database systems, which meant that you needed to do normalization and everything. It was basically one of the first things that I was forced to forget when I started doing big data. So keep in mind, data duplication is not bad. It actually gives you performance because data storage is cheap. The price of storing data is much, much less than taking your time in order to structure the data to fit in something. Okay, let's have a look at data models. So you have a relational database model. Who doesn't know what a relational database model is? Everybody does? Okay. But there are different ones. There are key value stores, which is like the easiest one. We will explain them in a minute. There's a document data store or document data model where we store documents in there. It's a sibling of key value store, more or less. We have a column family model, which is basically one of the hardest ones to understand. And people always get them wrong, especially in implementations in organizations. And then you have the graph model, which is pretty neat thing. It's pretty cool because it makes sense from a human perspective. So let's get started on key value stores. So this is a small example of what a key value store looks like. Anything special you notice? No way? Well, for one, I see that one record doesn't necessarily have all the data of a record or all the data of a specific entity. Like users 214 here, I see that thing coming back in all of them. So actually, if I want to have the full view of that user, I need to retrieve multiple of these values. I need to retrieve multiple of these records. But a key value store in essence is pretty simple. You have a key and you have a value. That's it. But key value stores are fast. They're really, really, really fast. And they're fast because they're very easy to query on if you know the ID. They're optimized to query by ID. Any other sort of query that you want to do is not possible. You can only get the value for one specific key. Sounds like a pretty lousy database if you ask me. But there are use cases. Take a website, for example, where the key can be the URL and the value can be the actual web page. Everybody who wants to go to a specific web page already knows the address. This is what caching databases are made for example. If you want to have a cache most of the times is a key value store. There is one more thing that you can do with a key value store. You can scan. You can actually say like, okay, I start here and give me back every record that starts with users 214. And I get everything back. So the moment that I have users 215 here, for example, then it will just stop and say like, okay, all above is what you need. One important thing to understand is that the value and the key can be anything. It can be audio, it can be video, it can be plain data, it can be just a bunch of bytes. It doesn't really matter. It can be anything. And that as well provides you with a tool that is pretty interesting when you have to deal with data in upcoming exercises. It's also very easy to scale because there isn't a relationship between the keys most of the time. If you want to do range scans over here, then it's something different. But you can, if I want, I can split this data very easily across multiple machines, across multiple nodes. The only thing that I need to do is split it. As you will see later on with different data models, this is going to be a lot more difficult. Now, if you want to, some stores provide ordering, which means that the keys are ordered. And that usually is, the moment that you have ordering, that's a difficult one. Because that means that there is a dependency between records, and that's hard to scale. So most of the time, key value stores are used for caches or for configuration stores. So if you want to store all your configuration on one location, if you know that you will only need to get your data by key, then this is the model that you should use. So when you look at what you can do with a key value store, these are the methods. So you can actually scan, like I said, just scan through based on a common prefix or whatever. You can do a get. So get the value of a specific key. You can do a set. For this key, this value should be set, which overrides if needed. And you can do a delete, which basically means remove the key value entry from the key value store. Anyone any questions about key value stores? Nope? One thing that you often see is that they use a date, for example, in the key, because then they can scan and they basically get a time series. There are all kind of tricks that you can do with only the keys of a data store. But we saw that sometimes, it's not efficient to only have a key value store, right? Because I have multiple values. It meant that I had to do multiple retrievals from my data system. And I don't want to do that. I want to get richer documents. I want to get richer information. In which case I can turn to a document store or a document model, where usually you have a simple key, which is a string, which is a number or whatever, but you have a complex document. So it's actually a key value store where you have a document as a value. Now that document has some sort of structure, but it doesn't necessarily need to have the same structure every time. As you can see over here, Wim doesn't have a birthday, and I don't have a company. This sounds a lot like a relational database, where you would just have a record in a table. But the main difference is that your record or your records don't necessarily need to look the same. They don't even need to have the same values in there or the same fields in there. If you want to do something similar in a relational database, you can create a record with all possible fields in there and use that. And we see that happening. That's the tricks that people do on relational databases. The only problem is that even the empty fields are taking in storage. In this case, if there is an empty field, there is no storage. Nothing is stored there. So document models or document data stores are very often combined with a search index. Because you have that value, you need to be able to search through them and to have a richer way of retrieving data. Which means that in a lot of cases you have a specific query language that you should use or could use. Who has heard of Elasticsearch? Elasticsearch is a pretty good example of a document store for it. You have the query language and you have the ability to store documents in JSON in that case. And you can query them through Lucene or through Lucene search syntax. The only problem with that is that your index needs to be kept in sync with your key value store. Now, what you get in return is a store where you can have any kind of key again, but your value is a structured type, which can be JSON, XML, BSON, which is a binary variant of JSON, or anything else. I've seen people put CSV in there. Please don't. It's not a good idea. But scalability requires caution. It isn't as easy to scale this as it was with a regular key value store. You might have relationships between documents, although you try to limit that as much as you can. And scaling your search index also becomes a hurdle. It becomes difficult. This is something that, for example, Elasticsearch has done very, very well, is the ability to search. They do sharding, but basically they search on every single shard and then aggregate that data together again. So most use cases for a document store are search engines. Think the thing that you push behind the website. Go to Amazon and look at all the books or search for a book, and you will get a list of all characteristics of books, like genre, like amount of pages, like whatever. that is all provided by a search index. The other thing that document stores are good for is for real entity data stores. And with entity data stores, I mean, if you have to build an enterprise application, you can store your data into a document store. There's no problem in there. Just don't try to normalize it. Make sure that your documents contain all the data you need, or as much data that you need, or that you can put into it. Like for example, if you have an invoice, usually if you look at a traditional relational system, if you need to model an invoice, you will have an invoice header, as it is called, which holds who is buying it, the total usually, the date of the invoice. And then you have a set of invoice details or lines on your invoice, basically saying this product, he bought that many of them, and this is the amount, and this is the total that we get out of it. If you want to retrieve that information, let's say that you have bought 10 different items. It means that I have to do 11 queries on my data system in order to get all my data. I need to get the header, which is 1. And then for all the 10 lines, I need to retrieve that data as well. Truth be said, you would just write one query where you do a join. But you will hit your data system 11 times. When you do this in a document system, you're basically making an invoice document. And that invoice document contains all the information, also the lines, also your invoice lines. So the moment that you need to retrieve a document, it actually means retrieving one big blob of data from your underlying data store. So when you look at what is possible with a document store, you can do a find by query, which is, the query is most of the time is technology dependent. So there is no such thing as SQL for document stores, although people try to build a layer on top of it to make it possible. But usually you have to query it in a language that is specific to the document store. You can do a get based on a key, which is basically the same thing as you would do with the key value store. The create is also very similar, or the set. You can do an update where you provide the key, so which document you want to manipulate, what you want to manipulate, and into what you want to manipulate it in. And you can do a delete, again, on key. Understand that if you do a create, an update, or a delete, or any modification to your document store, it means that not only your backend key value store needs to be updated, but also your index needs to be updated and kept in sync. Often these two things are two different things. It's not done at the same time. Because the indexing, or modifying the index, is a very heavy operation. So most of these document stores, most of these technologies that implement a document model allow you to do a lot of inserts and postpone the indexing of the newly created or the changes to a later date or to a later moment, and put some sort of delay in there. Anyone has a question about document stores? Nobody?
The results are always documents, or
Sorry?
the result of the query is always a document?
The result of a query is always a document or a list of documents. It could very well be that you just give me all the documents which have an age field that is larger than 15, for example.
Part of the document, so the document as a whole.
Yeah, and it returns the whole document for you. So basically it's a secondary index that you have. So your primary index, like you would have a primary key on your in a relational database, that's the ID. But all the secondary indexes, like you would have secondary indexes in a relational database, are pretty similar. Also, if you do it in a relational database, if you query on one specific field, you will also get back the whole field, the whole record, right? That matches. So this is not different.
We lost SQL as a language in development.
Sorry?
So we have lost SQL as a language to query, but it's more difficult to query the document in an efficient way, because SQL is kind of abstraction on
Well,
on the table, and here we manage directly the document. So, for example, the order of the query, the order we do the processing for all the document, is row on data, or there is some kind of engine.
so you have a way of searching, but the way of searching is specific to the data model. We will see graph stores in a minute, or graph models in a minute, which you simply cannot query with SQL, because you're going to ask different questions to it. And this is the same for a document model. You have people who have built a layer on top where you can actually put in SQL, and that SQL will be translated into the specific language being used for example, Elasticsearch, or for MongoDB, or for whatever other store that you decide to use. But in essence, most of the time, it's the technology that defines what kind of query language that you can use.
Business related. The model is the way we define the object in the table,
Mhm.
the collection is strictly defined by use case.
Yeah.
There is no point of doing like any kind of depends on the question we ask.
Indeed, that's that statement that I showed you. Indeed. So you have to wait until you know what kind of question is being asked before you can decide what kind of model that you're going to use. In reality, you will see that you will have overlaps over there, right? You're not going to create the same graph model multiple times because you have multiple projects or multiple questions for that. You're going to reuse that as well. But it is the request that defines what kind of data model that you actually want that you're going to employ. Most of the time, the more or less generic model that you would use, so if data comes in, you would just store it as even a sequence of bytes or a CSV, or you have formats that are more ideal for that, like Parquet, like Avro, like the other ones, org files, whatever, that have the ability to store a huge amount of data in a very efficient way. And then you can still decide to transform that into whatever you want or whatever you need. Okay? I switched column stores with graph, or column family stores with graph stores, because graph stores are easier to understand. Column families are really, well, you need to get your head around it. But graph stores are pretty straightforward, because there are not that many types in there, or concepts in there. You have a vertex and you have an edge, and you have properties, and that's it. A vertex or a node are the circles over there. So the 1, 2, 3, 4. You have properties which are linked to a vertex. And you have relationships which basically link one vertex to another. So what is different between this and a relational model, for example, is that your relations are a first-class citizen. They are explicit. You can actually already put properties on your links, on your edges, on your relationships. So for example, this one models basically a course where you have a student and two tutors, and you can see that there is a relationship between multiple of them. Now, if you want to know all the people that else is connected to, the only thing that you need to do is traverse the edges. If this would be a very large graph, and I think in one of the next sessions you will actually see larger graphs and whatever graph theory that comes with it, you'll understand that this is something that's really, really powerful. You can create a social graph with this and basically say like, who is connected to me? Am I connected to that person? And who is in between? And why is he in between? Is it because he bought a product? Because that means that there is a relationship, bought product, and the other one bought the same product. Maybe we can set something up. If you want to analyze relationships much more than the entities themselves, then graph stores are very, very, very interesting and very powerful. Because they can do that traverse, they can do that analysis of the network itself very quickly and very efficient. Something that would take like hundreds of queries in a relational database could be one statement in a graph store. So in graph stores, the relationships are your first-class citizens. This is what makes this special. This is what makes it different from all the rest. Because if you look at a relational database, you just have records in a table. If you want to have a relationship between one record and the other, the only thing that you need to do is explain that this key is related to that key. That's it. It's not explicit. It's a convention that you use. In graphs, it really is specific, and you need to define them. Just like you define a record, you define a relationship. The type of the relationship, and maybe some properties, like weight, like whatever. It also means that it's very easy and cheap to update relationships. Something that is unthinkable if you want to do that in a relational database, because it requires you to do the whole reprocessing of the data that you have. It could very well be that one record or one entity type or one node in this case, right, has different kind of relationships than another node which has the same type. In this case, you can see that me as well as else, we're both of the type tutor, but we have different relationships. We teach the same thing, but I have a friend relationship, and apparently she really is another friend of mine. So that is something that's, I think, not even possible in traditional systems to model something like that. So as I said, you have a node with properties and you have an edge, which can also have properties. For example, has any one of you used a graph store before? Anyone who has used something like this before? Who of you has a car? Who of you has a GPS in that car? Or has a GPS on its phone? GPS is using this kind of thing, where roads are being expressed as nodes, crossroads are being expressed as nodes, and your roads are being expressed as relationships with weights. The amount of lanes that you have on a road can be a property of an edge, for example. So if I need to go from A to B, I can very quickly determine how I should be going, because that's just graph analysis. And there are a lot of tricks that you can use when you're doing graph analysis. But it's hard to scale. And it's pretty obvious why it is hard to scale. Because everything is related. You have a lot of relationships. So if you need that to split that out of multiple machines, it becomes, yeah, you require deep knowledge to know what would be the golden cut, what would be the most efficient way to cut the network, where I want to cut as little as possible relationships or edges. Because the more edges that I would cut, the more communication that I will need to do.
It is not always you need to understand the sense that you have that you need to scale, the word scale. What do you mean for scale?
So scaling means, so there are multiple reasons why you want to scale. So it could be that all of a sudden you have like 1 million users that you need to provide. At that point, that single machine that you have is not going to do it anymore. You can try to buy a bigger machine, but even that is going to go up to a certain limit, because at some point you're going to pay huge amounts of money for just a little bit extra in performance. That's why we say that in big data we scale out instead of scaling up. We add more machines instead of making bigger machines or upgrading the machines. Because in the end that is cheaper and it provides us linear scalability or close to linear scalability. So when I talk about scaling, when you scale out, you need to make a decision what data you're going to put on which systems, on these nodes. So you need to decide how you're going to cut your data and put it on these different nodes. I could have taken the Lego blocks and gave it to one person, but it would take ages for him to complete. I can distribute my work across all of you by giving you a piece of the data, and it will go much faster. Because each of you can do the count and report back, this is the number of blocks that I have. And then I just need to do the aggregation, and we have the number. So that is scaling out. We scale out to make it possible to store more data or to be able to service more requests or to handle more requests. It could very well be that our system is not capable, or one system is not capable to handle the load, to handle the amount of users that are asking questions from our system. That's also a reason to scale. Basically, the moment that you get into often related to the hardware-specific part of the system, you need to scale out. You need to scale up. You need to scale. The difference for big data is that you scale out. Traditionally, we would scale up. But by scaling out, we basically say we want to mitigate the risk of something going wrong. Because if you look at large organizations, what do? They buy a very big data server or database server. And they put a lot of effort in making sure that the system does not go down. Because if it goes down, the whole company is just sitting there and wasting time. Why do you do that? If I would give you 100 eggs, would it be the best idea to all put them in one big basket and walk around with it? Or would it be better that I give you all baskets and spread my risk? So that could also be a reason why you want to scale. Does that answer your question? Okay. So obviously, if you want to scale something that's heavily intertwined, that has a lot of relationships, it becomes harder because you need to decide where you're going to make the cut. So that you can actually take a part of that network and put it on all the different nodes that you have, or several different nodes that you have. That's the difficulty when you deal with graph stores. So use cases for graph stores, two that I can immediately think of is for social analysis or product analysis, where you want to understand how people use your products You want to see if there are communities. You want to see if there are flaws in your system. Can I disconnect the whole network by just taking one node out, for example? Those kind of things you can do with a metadata store, with a graph store. The other thing is a metadata store. A metadata store is something that is coming up right now a lot, because in the past few years people have been engaged into large big data projects and they started building solutions and they basically lost control. Because they have so many processes running, data is in so many locations, they need to have knowledge on where the data is and what is handling that data. What processes, what do we actually do with the data? I challenge you to go to any organization and ask them, like, what are you doing with my data? You're allowed, because that's GDPR. Go to any organization, please. It's always very, very fun to see their reaction. Because that's hard. We didn't build the systems to get a grasp of what we're doing with the system because we were interested in the end result, not in the way how we got there. So that's where metadata stores come in and allow you basically to define everything that you have when it comes to data in your organization. So when you look at what you can do with a graph store, you can link two nodes. So every node usually has an ID, right? And you can make a link of a certain type between two nodes. You can unlink them as well, so remove the relationship. You can get a node by ID. You can set a node, which basically creates it or overrides it. Or you can create, or you can delete a node. In most cases, you cannot query for a node based on properties. That's not what a graph store is meant for. Usually you know one specific location where you should start. You pick a node in your network, which can be the store, for example, or it can be a specific customer, and you start traversing from there. You start analyzing from there. Which means that you already know the node ID. Now, that wasn't a sufficient enough answer for a lot of people. So right now you see a lot of graph store vendors actually implement the search index next to it as well. Because then it allows you to search for properties or to search for nodes with certain properties. But looking at it from a pure standpoint, then you're probably using your data store in a wrong way. Anyone any questions? So if you want to play with graph stores, I encourage you to have a look at Neo4j. They have a lot of tutorials to explain you how you can actually leverage graphs to do your analysis. One of the use cases that they have is a movie database where you can actually see like who was co-starring with Robert De Niro, for example, in which movies. So you can actually write queries that will analyze the whole graph and come back with a list of those people. It's quite interesting. It's fun to do.
Could you please spell it?
Sorry?
Could you please spell the name of?
Yeah, I'll just write it down over here. I'll give you an example for all of them. And if you want to play with it, then so key value stores. Who has heard of Redis before? Redis? Yeah. The second one was a document store. Look at Elasticsearch. I think that's the easiest one to get started with. The most complete, and you will find a lot of information from it, for it. Then you have a graph store. That's Neo. For J. And then the last one is a column family store. And a good example is Cassandra. Especially the last one can be tricky. Can be tricky to set up. For people who have knowledge of Docker, you find Docker containers for all of those. So that should ease your deployment a bit. So, column family stores. Column family stores are a bit different. They look like tables, but they're not. And to make things more difficult, they actually implemented SQL on top of it. So a lot of people are using it in a wrong way. What is so different about a column family store? Well, it has column families. But what is a column family? A column family is a grouping of columns. But why would you do that? Obviously, I can group everything together that is related to my default information or my general information. I can group everything together that's related to my address. But that's not the power of a column store, of a column family store. The power of a column family store is that you can use your columns to put data in. These things. I have a column family called invoices, and my column name is actually the date of the invoice or the invoice number. The first time that I explained something like that to someone who's heavily into relational databases, he was like, no, you can't change column names. I was like, hey, yes, you can. Because right now, I can do a query and immediately have all the information, all the invoices, just by getting a single record. The power of column family stores comes from the fact that you can model data in your columns. You can have millions of columns easily. It's a very, 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 very powerful way of storing data, but it's very often misunderstood. Because people say like, oh, we can have that many columns, let's just model it like a relational database. And then all hell breaks loose. Because then they discover that, that you cannot do joins, or at least not efficiently. The idea of a column family store is that in one record, you will have all the information to answer your question. I can build a customer screen on a website with only getting one record over here. If I want to allow you to basically go to a website and see all your orders, all your invoices that you retrieved from or that you created in the past, I only need to do one query. I immediately have all the information. So when you look at a column family store, usually when you want to shard this, when you want to scale this, it could very well be that certain column families are on different nodes. So you can have one record, but the data for that one record can be split out over multiple nodes. Because you're going to shard on column family and not on the whole record. Why you want to do that? No?
Isn't that an extension of a key value store?
Sorry?
Isn't that is an extension of a key value store? It's more complex key value store.
One of the things that I wanted to get to is that all of these models are basically an extension of a key value store. Because all of them have a key of some sort and a set of values of another sort. Even your graph model can be modeled as a key value store, where you just have your relations as a record in your key value store. All of these are extensions of key value stores. In this case, your key would be the name, your row key, as they call it, your column family. That would be your key. And most of the time, they go even further and they make the key the key of the record, your column family, and the name of the column. That would be the key of your value, basically. So yeah, it is basically again just an extension on a key value store, but it's using a key value store in a different way.
In this example,
Mm-hmm.
if I understand it properly, the default family
Mm-hmm.
looks very much like a normal version database, while the invoices family is not only the fact that the column name changed, but also the content. It's more a document than a value.
Yeah.
Is it by chance or is normally the case?
You can store anything as a value. Whether it is a document, or it is an array, or it is a list again, it doesn't really matter. You can, it's diverse. Also, data that you have not filled in, and that's the consequence of this. If for some reason I have a record over here that does not have a specific column filled in, it will not be stored.
The column and the dynamic, we can
Yeah.
delete and update column.
In a lot of cases, you can even have multiple versions of the value of that cell.
Does it store empty values?
It doesn't store empty values because underneath everything is translated basically more or less in a key value store.
There is a unique ID for the row
There is
across.
Yeah, so this is the thing where you group all your data on. See it as the prefix that we had in the key values store. And then we say like, okay, default is the name of your family, and then name. So basically I can store this in the key value store as being customer/214/default/name is Daan Gerits.
But what if customers 214/invoice/a date where he didn't purchase anything?
Then it doesn't exist. That record does not exist. But if I want to know all the moments that he did purchase something, then the only thing that I need to do is give me customers 214/invoices, and I get back all of them, or all of the purchases, all of the invoices that have been made with their information. Now it is very powerful, but you only have a limited amount of column families, or usually you have a limited amount of column families. If you have more than 10, I would start using different tables, because in a column database, a column family database, like for example HBase or Cassandra, you will still have the notion of a table. You will still have a table, but that table will have records. But instead of defining what the record, so instead of defining these fields, the only thing that you define are the column families, because the fields in a column family, they're dynamic. Because you know what you will be asking. these models are heavily based on knowing what kind of request, what kind of question that you're going to ask from your data. You will model your data in such a way that it will answer your question. It could very well be that I have two different tables. One where I have all the invoices information and default and a key and whatever, and another one where I have more or less the same information but from a product kind of view. Product ID, product name, description, and all the invoices where this product has been, or all the customers that have actually bought this product. That could be a use case as well. Will I have duplicate data? Yeah. But that's not a problem. That's something that we will deal with when we're doing the processing. So, it might seem that these things are trivial concepts like a table and a row key and a column family and a column. But the biggest problem is that you might think that you know what they mean. It's not necessarily the case. They're slightly different. Like a column, putting data in a column, no sane database administrator would do that in a traditional system. But it all starts with people asking the question, what if we would do it? It is pretty hard to reason about. Because you have these dynamic column names, you need to very thoroughly understand what and how your data should be put in. If you try to build a generic data model in a column family data store, it's going to fail, I assure you. One important thing is that you have to optimize for retrieval. Seriously. If you want to build a big data system in the future, make sure that you get the data in, store it as raw as possible with the minimal of processing that you need to do, so you can make the minimal amount of mistakes, and then stop. Then go to the end and ask yourself, what kind of use case am I going to solve? And what would be the best data model to solve that? And start from there and work back to the data that you have. A column family data store is pretty fast. And it's pretty fast not only in retrieval of data, but also in storing the data. For example, a few years ago, well, actually more than a few years ago already, there was a metric or a benchmark of HBase, and we were able to do 125,000 inserts every second. The price that you will have to pay in order to get a traditional system with that kind of capacity is huge. One important thing when you're doing the reading is that you have all the data at once. You don't have to search, you don't have to pull or whatever. You go to that record, you get the information of that record, and you're done. That's also why it's very popular in analytical use cases. For example, I want to capture the metrics of my systems, in which case this record can be a system, and I can have like my 15-minute interval, my 5-minute interval, my 1-minute interval, of even a rolling number like -1, -2, -3, -4, -5, and I can have all my metric data in here. Everybody understands that? So you can put time-based data in this format as well by using your date timestamp as the column name and the data that corresponds with it as the value.
Question here.
Yeah?
Should the timestamp be the same for customer 1 and customer
It doesn't have to be. It can be, but it doesn't have to be. Because the columns, there is no restriction on the columns. When you describe a table, you only get back what column families that you have, not what columns that you have.
But some place would be empty if
Yeah. Could very well be. You have to take that into account the moment that you retrieve the data.
Going back to the example you mentioned before, if we want to retrieve on the one side the invoices of one customer, and on the other side, because we try to improve the system for retrieval of information,
Hmm?
and on the other side, we want to extract all the customers who have bought the product, it means that we will need to store the information twice.
We'll need
We
that?
need to store the information twice.
Yeah. Because at that point you're asking the question from the perspective of the product and not from the perspective of the customer.
And then it also means that whenever there is a new invoice,
You need to update both.
we need to have it's a synchronization
Yeah.
that there might be all the no issues, but there might be a bigger effort to have the data properly synchronized.
Yeah, indeed. It is, you have to take that into account the moment that you do that you update both of these things. So it means that it could very well be that one modification leads to multiple writes in multiple tables. But that's the same thing. It could very well be that one organization has a columnar store and a graph database and whatever else they need. If the data comes in, at some point, that's what you can build. You can do the modification in all these systems at once. But you need to cope with moments that things go wrong. For some reason, I could not write it over there. What am I going to do? Am I going to remove it in all the other systems or not? That's the hard part of data engineering. So what can you do with a column family? You can scan. Okay. You can scan based on the prefix of your row key. So give me all records, give me all rows with that specific column family that are prefixed with this specific string or whatever. You can do a get, in which case that you will do a get with the row key and which column families that you want to retrieve. So it could very well be that if you do a query, that I only want to get the key and the invoices and nothing else. I don't want to get the default information, or the other way around. I can do a get where I get the key and the default and not the invoices. I can do a set, and that is actually a mistake because you have to explain the column family there as well. You set for that specific key, that column family, you set this specific value. And you're missing the column there as well. Sorry. So for that key, for that column family, for that column, that's the value. And you can do a delete by key, column family, and column. Based on what you fill in, data will be removed. If you say, I do only delete by key, if you do a delete by key and column family and column, you will only remove that specific column. That's the kind of interface that you can expect when you talk to a column family store. Any questions? If you might have questions next time, just ask me. I'm here on Thursday again, so let it sink in, and if you have a very cool way of manipulating this stuff, I'm very eager to hear it. But let me give you a bit of advice of the things that I've learned. So, one important thing and that is strange because it isn't how we used to consider data systems, is that your data model for writing data can be totally different than your data model for reading data. People who build applications might see this as CQRS, or might understand this as CQRS, which basically means that there is a different flow, that there is a data model that you optimize very heavily to write data into, and that you have a different store which you optimize to read data from very efficiently. And you have a process in between to get the reads from one and write it into the other. Keep in mind that I use the word data store here in a very broad sense. Another one is always start from the question. I've mentioned this many times right now. So start from what you want to accomplish and work back towards your data, not the other way around. There are so many organizations out there that basically have a goal of building their big data platform, which is total nonsense. Do not spend too much effort in trying to make it fit into, or make your data fit into a specific model. It won't. If you want to have the real power, store it as raw as you can and move on. Another one is that if you need to do a join, you probably did it wrong. Which means that if you're using a graph store, well, graph stores, you're not joining anyway, but if you have a document store and you are doing joins in there, then probably you're doing something wrong, because it's not meant for that. Store your data together. You have not started from the question. You have started with the data that was offered to you, and then indeed you need to do joins in order to get everything together that you need to present in your application. But if you started with the request, there's no reason why you should do joins. Correction, there's hardly a reason why you would do joins. There are some of them, but most of the time. Any questions? Because this is the last slide.
When you said to store in the raw, most raw format you can,
Hmm?
can you give us some examples?
I have a system, an external system, which I use to track customer complaints. And I can integrate with that system because they give me a dump every night of a JSON representation of their data. Every ticket that they create is a new JSON object. I could say that I start restructuring that in a common format into the way that I see it, what a ticket means for me. But I'm not going to do that. I'm just going to get that information in and store it as is on my data store. The most thing that I would do, and even that is sometimes not, that's certainly not encouraged, is change date formats. That I know that we are talking in, for example, time zone stuff, or character encoding, which are more of the technical things that you want to get aligned, so you can read it more easily. Another example is my company has an integration with a logistics partner, and the logistics partner gives me back track and trace records of the packets or the parcels that I sent with it, and I get it in as a stream continuously. So every time something changes with one of my parcels, I will get a message in. What I will do is just store these messages raw on disk, raw in whatever kind of data store that I have. I'm not going to manipulate them. I'm not going to translate them in something that has a business meaning for me. Because I don't know what kind of question that I'm going to ask. It could very well be that I'm more interested in the trend of the messages that I get, instead of the actual value of the messages. So the moment that I get a question, I know what kind, I know the context in which I need to analyze my data. I know the context in which I need to process my data to get that information out. Is that?
I can imagine it, but okay.
It's, you need to get data from a system anyway. That can be any system. That can be human input, that can be...
I know, but for me it looked like a mess. It looked like all data.
Yeah, and it is. But it's your processing that will basically transform that mess into something else. And the thing is, in the beginning, you will take it together. Obviously, the most structuring that you will do is more or less technical structuring, because you know that it came from that source, so you're going to take everything together in that directory, for example. So you know that all the records, they more or less have the same structure. So if I need to read that information, I know that I have to build an application that reads that kind of information. So I know I have predictability on what kind of input that I get. But even then, through time, the format of the information that was sent to me can be totally different. Another one is a web crawler, for example. You crawl the internet. Nobody does that anymore, except Google. And you need to store that. You're going to store the HTML that you crawled as is. You're not going to retrieve all that information out, because you do not know what kind of information that you need to get out. So the first thing that you do is just store it in the rawest way possible, which basically is like a large string, a large text fragment that you put in your data store. Because the next steps are going to be to clean it up, to extract the information out of it. But it all depends. Even through time, the website changes. So the thing that you have written to extract information from it doesn't work anymore, because the structure of the website changed. So you need to modify your algorithm to extract data from it. Or maybe you made a mistake. Instead of a date, you thought the date was in seconds and it was in milliseconds. And all of a sudden all your dates are incorrect. At that point what you can do is you can remove the stuff, the results that you have, the wrong results that you have, and you can start on that raw data again and start reprocessing it. And that way you are protected against human fault tolerance. Because most of the time, if you would do that in today's organization, you have someone running for the tapes and for the backups, and you will most likely lose a day, maybe, of data.
How you decide in which system you store the raw data?
There are a lot of criteria. Like for example, the tendency right now is to store data in a system with the least amount of moving components to limit the amount of risk that you have, which means file system or something similar. Because you're reading stuff in batch, a file system is not that bad. Look, S3. Who knows S3 here? So AWS S3, scalable storage. S3 is used as data storage in a lot of cases.
Basically, you have such a system to store the raw data,
Mm-hmm.
and then depending on the question that you have to answer, you will decide which of these type of technology is more convenient.
Yeah.
For you.
Yeah.
And you build this on top of the
You-
data storage.
What you usually do, or what I tend to do right now, is you know what a view is in a database, in a relational database? My views are data stores, which actually means that I can have my raw data coming in, and I have my graph database, I have my document database, or key value database, which means that I have a process sitting here that will transform that. But usually I have a first case. So let's say that my first case was a graph database. I created a process that would get the raw data and transform it into my graph data store. But the second time I discovered that there are things that I have to do similar. I need to clean the dates. I need to get some additional information. So instead of doing everything again, what I'm going to do is I'm going to take the logic out of here and work like this. And the more cases that you're going to implement, the more of these you're going to have. The more places you will have where there is logic that will actually transform your data from one thing in the other. Raw data systems, in the past, and for analytical big data means that you do big data in order to get insights into the data. You have operational big data, which is actually meant to actually do something with the data.